my name is Julian. In this lecture, we will talk about the stiffness of material and the loading on structures. So stresses refer to the strength of the material. That is the amount of loading a structure can withstand before it breaks. However, this must not be confused with stiffness. Let me explain using an example, the Helios solar-powered aircraft as developed by NASA. As you can see from the photos, the wings are very flexible and can bend greatly. These wings have low stiffness, resulting in a shallow slope in the stress-strain curve. If we take another look at the stress-strain curve, you can see two curves plotted here. One curve has a high ultimate stress and one has a much lower ultimate stress. However, both curves have the same linear slope and therefore the stiffness is the same. So the slope of the stress-strain diagram indicates how flexible or stiff one material is compared to the next, but it says nothing about its strength. If you take another look at this diagram, you can also see that the upper line has little deformation before breaking, whereas the lower line has quite a large deformation before failing. This is indicative of another set of material properties, whether a material can be classed as ductile or as brittle. This is easiest illustrated by looking at these chocolate bars. If I try to break this first bar, you will see that I can bend, twist and even partially draw it apart before it breaks. However, if I try to break the other bar, which is a different type, it simply snaps into two. This first chocolate bar can be classed as ductile. The material allows for a lot of deformation before breaking in two. The second bar, however, is classed as brittle and allows little to no deformation before breaking. Materials can therefore be classed as ductile or brittle depending on their behavior leading to failure. Other examples of ductile material are aluminum and steel. Examples of brittle materials are glass and polymers, such as the one used in carbon fiber composites. Now so far we've talked about a force acting on the material, either extending or compressing it. These are, however, not the only types of loading we will encounter. Let me take you through them one by one. The first loading type is compression. This means an actual force is applied to the object, compressing it, and as a result the object becomes shorter, as you can see as I compress this foam cylinder. Hence, it's often denoted with a minus sign. The next loading type is tension. This is an elastic band. We again apply an actual load, but this time it is directed away from the object, and as a result the object becomes longer. This is why tension is often denoted by a plus sign. That leaves us with two types of loading remaining: shear and torsion. Shear is a transversal force acting perpendicular to the longitudinal axis of a beam, or in our case a spring. Finally, there is torsion, in which the structure is twisted along its longitudinal axis. Stress is defined as load over area without specifying the load. However, the type of load determines the type of stress that can occur. Stresses can be divided into normal and shear stresses. Normal stresses occur when an object is loaded in tension or compression. That means the load is applied perpendicular to the surface of the material. If we then again look at the stress-strain curve, we can now define the linear slope in the diagram. This slope is known as the modulus of elasticity, or Young's modulus, and is known as the measure of material resistance against imposed elastic deformation. Mathematically, it is defined as the normal stress sigma over the normal strain epsilon. When you extend or compress an object in one direction, it often contracts or expands in another direction. If we assume that the overall volume of the object remains constant, we can observe a second strain in the transverse direction of loading. This strain is called transverse strain, denoted by epsilon t. It is equal to minus nu, to indicate opposite direction of deformation, times the normal strain epsilon L. Or, if further written out, to minus nu times the normal stress over the modulus of elasticity E. The small Greek letter nu is known as Poisson's ratio, and like the modulus of elasticity, the Poisson ratio is a material property. The other loading types we discussed, shear and torsion, cause shear stresses. Only these stresses act along the cross-sectional area instead of perpendicular. What would happen if we have a shear force? Let us take a look at this book. On the side of the book where you can see the pages, I have drawn a square and a diamond. If I apply shear force to this book acting parallel to the cover, you can see that the square and the diamond on the side of the book change shape as the pages start to move with respect to each other. The diagonal of the square becomes longer and the square becomes diamond shaped. The diamond shape contracts with two parallel sides coming closer together and the other set of parallel sides moving further apart. If we examine this more closely and cut an imaginary square from our beam under the shear load, we get a small cube that has parallel forces acting on it on all sides, forcing it into the diamond shape you saw earlier when I applied the shear force to the book. The shear stress, denoted by the lowercase Greek letter tau, is now defined as the force F acting along the surface divided by the area A over rigid X. The shear strain, denoted by the lowercase Greek letter gamma, is defined as the shear stress tau over the shear modulus G. Like the modulus of elasticity, the shear modulus is also a material property. For isotropic material, the modulus of elasticity E and the shear modulus G are related. The shear modulus G is then equal to the modulus of elasticity E divided by 2 times 1 plus the Poisson's ratio nu. And with isotropic materials, we mean materials that have identical properties in all directions. In practice, materials are often loaded by multiple load types. So, if we consider the case of a two-dimensional element that is loaded in shear and in tension, both shear and normal stresses occur. This is known as a 2D elastic stress-strain condition for uniaxial shear deformation, and this stress state is very common in aerospace structures. So now you know what we mean by stress and strain in engineering. Hopefully, this will help you understand how and why structures deform and allow you to design and select materials based on their material properties.